Thank you. Okay, yeah, hi. We're from Onego Bio. We're part of the EIT Food Think Tank. Just saying hello for the other EIT members. Yeah, but Onego Bio is a US-based Finnish company providing egg white proteins as an ingredient. Just a few words about our product, but then I'll get into the little bit more science and technology and bioprocessing. So of course, we're making bioalbumin, which is a recombinant protein that would be in egg white, ovalbumin. And some important things to keep in mind, of course, when producing a product like this, of course, the performance of the product, the egg white product has to be basically working just as well or better than the chicken form of the egg white. So that's one essential component. It has to work. It has to taste neutral or very similar to the egg. And also very important to have a kind of a cost parity as well. Like no one's really willing to buy an egg product because if it costs twice as much, it's less likely to be used. But one of the beautiful things about the egg white has been the price of the egg products because of the avian flu, for instance, that has been going around. So this is something that has definitely impacted the food stability, food security, and actually being able to provide a stable pricing for a product through this fermentation-based manufacturing method. And then also the supply resiliency. Of course, it's not good if the price and the availability of the egg white, an essential food component, is lacking in some cases. So that's something people rely on a lot. And of course, there's sustainability benefits of doing this. Of course, less greenhouse gas emissions, basically less land use for the kind of carbon feedstock that you use to make the fermentation-based product versus a chicken. So there are some sustainability win-wins here. Uh-oh.
Doesn't work?
No. Maybe you have a magic.
I have a magic.
Okay, beautiful. How do you do that? Seriously.
I can do it for you. You just tell me.
Go back one slide.
That is a challenging one.
Oh no. See? Okay.
I can only go forward.
Okay.
I'm magic one way.
Totally fine. Let's start here. This is great. No. Totally fine. So in this environment, of course, there's lots of alternative proteins. I'm not going to go into all these different options for alternative proteins. Of course, there's plant-based, there's biomass, what we call precision fermentation, although it's basically outgrowth of industrial enzyme industry, been able to cultivate in a bioreactor something like an animal-based ingredient that you can now make in fermentation process. And of course, there are cultivated meat, what was just earlier discussed. But I will focus mostly now just on precision fermentation or just fermentation-based food ingredients to give an example. Otherwise, this is too broad of a scope. But I'll focus just on precision fermentation process. Of course, this is probably nothing new to you, but just to describe, of course, you use a feedstock, which is potentially a corn sugar or a sugar-based carbohydrate to feed to the microorganism that you're growing in a bioreactor, what we call an upstream process. We find good conditions in the bioreactor to grow the microbe that would produce the product. We always then downstream process, or often downstream process, the product away from the biomass and also do some polishing on it to make it very clean and pure, and then also spray dry it, for instance, to make a final product that is very familiar to the consumer or to a food manufacturing company. Like if you're making egg white, you should also make an egg white powder, for instance. So you get a final powder. Okay, but that's the general concept, but I will spend a little bit of time talking about the base technology because it's sort of important. Considerations for doing this scale up. You should actually have a good technology, a good microbe that has good characteristics. It produces high levels of product, it's scalable, it has low requirements for production. These are sort of some things I will get into. Of course, developing the process to find a very cost-effective and scalable technology that can actually make something at a price point that is affordable. Otherwise, no one will use it, and you won't have the impact. And something that is kind of obvious, but I don't know, I mean, just reading some things about why startups may fail often is that if you scale up too early, was it 70% of those companies may fail because it's just very expensive when you start manufacturing. And if you're manufacturing at the wrong cost, it's quite detrimental. So giving that foresight to knowing what it will cost, very important to have calculations already for your technical economic calculations to support the planning needed, because it isn't necessarily, well, in this case with precision fermentation, a lot of this is built on industrial enzyme industry. We know what the microbes do, we know how much it costs, been doing it for 50 years, making, like say, capsaicin or something like that, which is a cheese-making enzyme, for instance. You can look at these examples and plan economically what it might cost. Boom, so you have many options, and it really depends on the product you're trying to make. I mean, there's really no right solution, nothing like that. But of course, given the whole spectrum of things, there are bacteria, there are yeast, there are filamentous fungi. Each has its own benefits, pluses and minuses. Some grow more quickly, some are growing quickly, but they have certain requirements. Maybe they need methanol for expression, or they grow a lot of biomass. We tend to like products that are systems, tech solutions that are secreted, a secreted product. So I'm going towards the ingredients here that, of course, it makes it easier to work on a protein if it's secreted into the culture medium. As well as something with filamentous fungi are also well known in this field in industrial enzymes, for instance, for secreting heavy amounts of enzyme, for instance. So there's a lot of different technologies here, and I will kind of look at a couple of these options, but again, just to give you a flavor for what options you have available as technology, microbial technology for your product manufacturing. So one thing to consider is the morphology. So how do the cells look? Of course, bacteria are single cell, and they're easy to grow, and they kind of have this very defined single cell sort of morphology looking, and the yeast are little cells like this, and these tend to, of course, be easier to stir. So if you're stirring it in a bioreactor, like the aeration, the stirring ability of something is less viscous if it's kind of singular cellular. But some of the filamentous fungi can be very filamentous, and it's kind of like, really slowly turning, and it's kind of very viscous. So that could be a negative thing if you are thinking about manufacturing in the later on. That requires a lot of energy. It requires a lot of oxygen transfer, a lot of mixing. But you can genetically, or even just by mutational working. So a filamentous fungus, for instance, can be very filamentous, but you can actually find mutants that become shorter, so hyper branched. So you can actually do that and select it. So many of the industrial enzyme strains for filamentous fungi are hyper branched and short. And the other reason is that the more tips you have in a fungus, the more secretion you have from the tip. It's actually German Spitzenkörper. So this is the tip of the filament that will spit out the product. So the more of those you have, the better. And also, if in a fungus, because that would be maybe one of the downsides to a filamentous fungus, is that normally it would create too much viscosity, and the oxygen transfer would suffer. So if you can basically make the morphology better, you can improve your whole process. So yeah, these are just some concepts to think about when looking at different technologies. One of the important things that one needs to think about is also the carbon input. So your feedstock that you feed to the organism, how is it used in terms of, is it just growing biomass? Or is it actually growing some biomass and then secreting the product? So there are kind of two different ways. For instance, if you grow a yeast or whatnot, you could grow this and it would just keep accumulating biomass. But remember now, the feedstock, your carbon source that you put in is kind of relatively expensive if you're just putting all your sugar into biomass. And I'm only talking now about a secreted ingredient product. So maybe some people for their biomass product would like that curve. But it actually, what we try to do is try to make it that we grow a certain amount of biomass, keep it at that state, and let it secrete. So the carbon coming in comes out as protein. So for instance, a good fungus can decouple growth from secretion. And that's actually really important because you should be able to convert, for instance, like 3 kilograms of sugar into 1 kilogram of protein. So kind of what is the conversion rate of your organism in your process? So this is kind of very important thing. So you're kind of avoiding just putting your sugar into biomass, making actual product. So these are important considerations. Yeah, very busy slide, but just if you look inside of a bioreactor, there's a lot of stuff going on there. There's a motor turning the impeller, and they're spinning around, and you have some liquid inside. You have, of course, some air maybe coming in, and you have cooling jackets on the outside. You have recording the temperature. You're bringing in different gases in and out. A lot of different things going on. It's extremely complex and really important so that we have bioprocess engineers. So they're very good at this and they will understand very well. But all these things are very important, actually. So considering what you're doing now, you're growing some living cells inside of a bioreactor. Well, the more dense your process is, the more cells are in the culture, the more demands there will be, right? So you actually have to demands of cell density, and also very importantly is the cooling of the tanks. On the outside of the tank, there are like cooling jackets, so you have to be able to take away heat, because a lot of biomass, a lot of living cells generate heat, and actually not in a good way, so you have to be able to remove that. Also the feeding of nutrients and the agitation that is creating the stirring, all these things are important factors, and I will say a little bit more about them. Of course, these all processes require energy, cooling, water, stirring, blowing air, all require energy. So just some comparisons of, just from some literature things that I was picking from the literature on yeast or Pichia, for instance. Say you have a 100 cubic meter bioreactor, and then you have quite a lot of biomass, cell mass in that tank in the yeast, so maybe it's 45 tons per batch, so a lot of biomass, whereas I was just saying with the filamentous fungus, you can generally use less biomass because it's more productive in that it's secreting things. It's better at turning over the carbon to protein, so generally speaking, you will have less cell mass, which is good, and I'll show you why. Then requires less cooling power too. So a yeast will generate a lot of biomass, and like I said, you have to cool that. So it could use up to 600 kilowatts here just to cool that tank. Process air that you need to blow in, of course, you're putting air in, aerating that, maybe adding some aeration. And in some really intense Pichia applications, you actually need to blow oxygen in there as well. Under certain conditions, that might be an option. And of course, with a Pichia process, if it's a kind of the AOX type of promoter, you even have to add some chemicals like methanol to that, which isn't great. So it's also flammable. So these are just some operational comparisons to different technologies. So it does matter a little bit which road you go down, because some of it's more expensive than others. Here's an interesting comparison. So as I said, you can look at these different ways. So for instance, what it really makes a difference is that, as I said, the lower amount of biomass, if you have a very productive biomass, let's say it's 20-30% of the volume, this is actually low, and that means, let's say that, okay, for this example of trichoderma, like able to make 100 gram per liter whole broth kind of production level of products. So what this means is that in a whole broth, 100 gram per liter, so 80 gram per liter is in the supernatant, and you still have some biomass in the bottom. So that's actually, when you empty this bioreactor, you'll get 8,000 kilograms of product out. Whereas if you're looking at this from a yeast, Pichia, for instance, you grow so much, if you, in this process, of course, in this process, if you grew a lot of biomass and you're only secreting less product, you probably only end up with something like 2,500 kilograms. So they're very different. So it really, like I said, there's no right or wrong answer here, but like for instance, this, if you're making with Pichia, if you're making, let's say, insulin for humans, totally fine, you know, this is all right. This is a well-accepted, approved method for manufacturing pharmaceuticals. But it's probably not a very, as you'll see in maybe the next slide, it's not very price competitive in terms of now food ingredients or something like a material protein or something like that. So just important to keep in mind, because there's, you know, this is something that is a consideration now. And these are, of course, just kind of thrown a bit in the air for comparison's sake, but looking at, let's say, a yeast process, for instance, just using the same numbers, let's say you use a 100 cubic meter reactor, maybe you make this 2,500 kilograms. You can't really scale that so much higher, and so in this case, I would say, you know, you can't really go to 250 cubic meters. But let's say, assuming you have a similar batch cost, of course, these prices can be anything depending on where you're doing it. Is this your own factory, or is this your contract manufacturing factory? But let's say 100,000 per batch for equally. Whereas now with the fungus here, you produce 8,000 kilograms, and also you can go to a larger scale with that. So this is also just an example of why scale matters, and depending on the organism you're working with. So you probably can't go to huge scale with a yeast or a bacteria, maybe. There may be something, but with the filamentous fungus, it's been done all the time. This has been done for decades already, so it's a known thing. So you can be down to, you know, $5, $6 per kilogram. And these are based on industrial enzyme pricing, so it's sort of known. So just important to keep in mind these costs. Okay, then just in scaling up in the lab, you know, we start with very small things, and we're going to larger things, and, you know, go to demos and full scale. So this is what it is to move into bigger vessel volumes. And just a little bit about the upstream challenges. So of course, the bigger you go with the bioreactor, the dimensions are changing, kind of the dynamics inside of the bioreactor are different, obviously. So just an example here, so there's a smaller tank and a larger tank. You can just see the kind of the surface area that you have to cool the tank is different. So here, there's a lot more space between the wall. So that makes a little bit of a challenge for cooling, for instance. It's a little bit different when you scale up to a bigger tank. So the cooling needs, the mass transfer, the mixing is different. And just an example of that is like when you're mixing something, every time you go bigger, the slower everything goes. It's kind of a philosophy. So in a small tank, if you put a tracer here in just 1 liter tank and you watch it mix away, it'll mix in really fast, right? And in the 100 liter tank, it's mixing a little bit slower, and this red color means a slower time, a slower mixing. Like it takes longer to mix that. So the bigger you go, the slower things happen, and that's very key. Okay, just some concepts too about what upstream scale practice is. So of course these are very highly empirical. It's sort of, you just have to kind of do it. It's sort of an experience. The bioprocess engineers are well known about this, but you can take several approaches. You can look at different constant power to volume or constant tip speed, different kinds of approaches to try to scale something. And of course, you can look into kind of a scale-up table, for instance. And this example from literature, this is an 80, you start with a 80-liter process and you go to a 10,000-liter process. And just one example here, so the idea is to try to set something similar. So if you want to set the impeller rotation N, this is the same as the bigger one. And what will happen there, so there's always a bit of a balance and a plus and minus, a compensation, which happens is that if you're just turning that impeller the same speed, well, what will happen? This kind of the volume energy ratio here. So this is actually kind of the agitation power. Things are agitating less, which is going to lead to maybe less oxygen transfer, less stirring and mixing. And now you start having problems with maybe there's not enough oxygen in the bioreactor and the cells are starving. So that's not good. So you have to think about another strategy. And as I said, the volumetric energy input, so it's a way to transfer the energy, the same agitation energy. If you use that approach, you're just putting the same amount of power per volume. And that will give you here, something a little bit more consistent. But then of course, you're turning that impeller a bit more, and that requires more energy. So there's never really like a equal win. You always have to put in something more energy, more air, more stirring. But this is sort of empirical. But again, these are just want to give you a flavor for this. I mean, we're not needing to go through equations, but just explaining how challenging this is at scale. And just to summarize some of the upstream kind of considerations, it's a lot about transferring the heat. In a bigger bioreactor, you need to transfer the heat away, so cooling that liquid, putting the oxygen in and air, and also the amount of stirring power that you need. And of course, not all of the organisms are scalable in that same way. So you have some technical reasons why you just can't go to 300,000 liters with certain, like a yeast, for instance. Maybe it's not that practical. Oh yeah, then downstream, so just a flavor of that. So downstreaming, meaning that you're purifying the product. And of course, if you're working now with some secreting organisms, that would be better. It's easier to purify, so it's out in the culture media. And now you just have to be able to purify it. And of course, if you have something secreted, it's just a lot easier to deal with. Some bacteria, which is fine if you have to use it, but then you have to break open the cells. There's DNA, host DNA, and there's other stuff dumped out into the solution, which makes some more cleanup necessary, and it makes the kind of regulatory thing a little bit more challenging sometimes. So, like I said, certain processes don't necessarily scale up that well, meaning the downstream. Sometimes you might want to purify a protein with a column chromatography, but maybe that's not going to scale up that well if you think you're now making giant columns where you need to purify. It works for pharma in a sense. They use big columns for things, but it's kind of more applicable to something like that. But here with chromatography, you start talking about big water volumes that you have to wash through in clean columns, or now when you filter things at a big, massive scale, those are giant filters, and you have to load them differently. And also that's the time that you think about scale up, you actually have to go fast. Because if you have a food product now waiting there for several days, you never know. The risk could be that it gets contaminated from the air, or something leaks in and your process is now ruined by some contamination. So you have to think about processes that are quick enough to go through rather quickly in the downstream. Yeah. So some considerations then, again, coming back to this point of technology readiness. So very early in the process, when you're making a food product, for instance, you maybe have your first version of your production system. And of course, that is relatively expensive. Just happy to make a pilot product, and that's fine for demoing it. But with a reality comes that, well, how long are you willing to invest in expensive egg protein or milk protein, for instance? So how long are you willing to do that? Because you have to have a viewpoint to, okay, in a year from now, we can get the costs down by improving the technology or improving the bioprocess. So, of course, then, as a startup company, if you're in a startup company, this is a very critical thing. You need to think about how much funding do we have to bridge the gap of being able to keep that going and sort of working through this maze. It's, like I said, a very key thing. So how do you get from a full-scale process that's kind of expensive to something cheaper that you can sell? Because there's really no point to making something if no one can afford to buy it. And also, of course, you can start working through contract manufacturing. Of course, that's a good idea to get it started, to have proof of concepts and show people you can make something, but ultimately, it does require, in many cases, one to build their own factory, for instance, because it's just cheaper to do. Of course, the CapEx is there, but you can combine these approaches. Yeah, and then just finally something a little bit about the regulatory landscape, of course. At least with Onego Bio, we have started our journey on that to apply to the US FDA. As you know, that the process is a bit shorter, 9 to 12 months, and the process is sort of defined and going through that. But in the future, we also are now looking into the EFSA approval for the ingredients. Of course, that process is taking a little bit longer time, and we're here in this conference now to hear more about the regulatory environment in Europe. There are different rules, of course, in Singapore and whatnot, but again, very important to consider. And likely, I like to say, at least with precision fermentation, it is pretty much like the enzyme industry and the industrial enzyme industry. So a lot of products already, similar things have been used in food processing already. So it's sort of, the organisms are well known to food industry, and the product themselves, like egg white. I mean, it's egg white, so it shouldn't be too controversial. But again, something to consider with the regulatory authority. Yeah, so these were conclusions. Just make sure the technology is ready, do your cost calculations and reflect on reality. How long are you going to be able to sustain spending a lot of money to produce something and hopefully somebody willing to buy it someday? But if you have the right combination of technology, processes, and scale, you can actually produce something for a low cost per kilo. And that's actually most applicable to large-scale manufacturing. Thank you.